Do you have my sound? Okay. We go to lecture 2, Internet Protocol version 4. We have TCP/IP protocol. You can see TCP/IP protocol. We have 4 layers. The top layer is application layer. We have simple mail transfer protocol in this layer for email. FTP, that is file transfer protocol for transferring file. TFTP, trial file transfer protocol. What is the difference between FTP and TFTP? You know? TFTP is trivial file transfer protocol, and TFTP is used to transfer a file either from client to server or from server to client without the need of FTP feature. Software of TFTP is smaller than FTP. That is trivial FTP. DNS, domain name service, for giving URL and getting IP address. SNMP, simple network management protocol, that is protocol for managing the network, and DHCP, dynamic host configuration protocol. In transport layer, we have SCTP, TCP, and UDP. TCP, transport control protocol, connection oriented, and UDP is Unidatagram protocol, that is connection-less protocol. What is SCTP? SCTP, that is abbreviation for Stream Control Transmission Protocol. Yes, Stream Control Transmission Protocol, that is a protocol in transport layer. In network layer, we have IP, Internet Protocol, that is connectionless, IGMP, Internet Group Management Protocol, and ICMP, Internet Control Message Protocol. And ICMP message used for diagnosis or control purpose. IGMP, ICMP, excuse me. For example, for getting the error in the system. ICMP, Internet Control Message Protocol, is a supporting protocol in the Internet Protocol Suite. It's used by network devices, including routers, to send error message and operational information indicating success or failure when communicating with another IP address. For example, when an error is indicated, when a requested service is not available or that a host or router could not be reached. That is error. But IGMP used for Internet Group Management Protocol. That is a communication protocol used by host and adjacent router on IP version 4 network to establish multicast group memberships. That is send message to the member of a group. Yes, that is multicast. And used by us and adjacent routers IP version 4 to establish multicast group. Yes, for multicast message. And ARP, that is address resolution protocol for converting IP address to MAC address and MAC address to IP address. Address resolution protocol is a communication protocol used for discovering the link layer address, such as a MAC address associated with a given internet layer address, typically an IP version 4 address. And the data link layer and physical layer include underlying LAN or WAN technology. Datagrams. Packet in networks, that is internet layer, are called datagrams. A datagram is a variable length packet consisting of two parts, header and data. The header of the IP datagram is between 260 bytes in length and contain information essential to routing and delivery. Here in this figure you can see IP datagram format. The 4-bit, that is for version here. If version 4, that is 0100, okay? The IP version 4. If IP version 6, that is 0110. And the header length, that is 4-bit, between 0000 until 5551111, between 0 and 15 words here, not bytes, okay? Each word here 32-bit, each word 32-bit, here 1, 2, 3, 4, 5. Option may be 0 to 40 bytes. If 0, we have 5 words. If you have 5 words, each word is 4 bytes, so that 5 words equal 20 bytes for header here. Header is small 20 bytes. And header is max 60 bytes here. Why? Because we have maximum 50 words. No. Because 1111, okay, this is 50 in header length. 50 words. 50 words equal 50 multiply 4, that is 60 bytes. Because each word is 4 bytes, okay? Maximum header size is 60 bytes here. So that header size between 20 bytes and 60 bytes. Then here DS is differentiated service here I will say, and ECN is explicit congestion and notification. And then total bytes here, total length of this data and header and data in bytes, 60-bit. Because that is 60-bit, we have maximum 2 exponent 16, okay, bytes. And the length of total length. Identification shows the identification of this datagram, that is 0, no use, don't fragment, say to router no fragment this packet into smaller parts, more fragment, we have more than here, and fragment offset, that is distance from the first of this segment, I say U. Time to leave, that is 8-bit, maximum 255, then protocol in the upper layer, then header checksum. And source IP address, 32-bit, destination IP address, yes, I say. And option between 0 until 240 byte. And this is payload. Payload, that is data that get from the upper layer, for example TCP, that is payload attached to each here. Header size, that is between 20 bytes. If option, for example 0, we have 5 words here, 20 bytes until 60 bytes. And total length, minimum 20 bytes, way payload is 0, and maximum 2 exponent 60 bytes, because total length is 60-bit here. The maximum is 65,536 bytes. So, version, that is 4-bit, current version is 4, next version will be 6, so that 0100, that is 4. Header length 4-bit, length of IP header in multiple of 4 bytes. This means in word, not in bytes. So that the header length may be between 20 bytes, this is 5 word. 5, this is 0, 1, 0, 1, okay, until 1111 word. This field between 2 values. Differentiated service or explicit congestion notification. This field was previously called type of service field. The role of this field has been redefined, but it's keyword compatible to type of service interpretation. Differentiated service, we have 60-bit, used to specify service level, but currently not supported in internet. This means when, for example, a router with mid-congestion, another packet will be lost. No important, for example, what is the packet? Packet of multimedia or packet of email. But in a protocol such as MPLS, we say later we have quality of service. And explicit congestion notification, ECN, that is 2 bits, no feedback, a new feedback mechanism used by TCP. Here. Now what is the ECN? I6 here. ECN explicit ECN, explicit congestion notification. This means inform previous router that we have congestion, and source decreases the sending rate. Source decreases the sending rate. We have 2 bits here, so in ECN, we have 2-bit here. If that is yes, if that is 00, that is non-ECT. This means packet is marked as non-explicit congestion control and not capable. If 01, that is ECT1, endpoint of transport protocol or ECN capable. And 10, that is ECT0, endpoint of transfer protocol or ECN capable. And if 11, that is congestion experienced. When that is 11, that is congestion experienced. The code 01 and 10 have the same meaning. This means the sending and receiving endpoints, are ECN capable, and no difference between 10 and 01 code. Okay, no difference. But differential service, that is 6-bit, that is code point, and 2-bit unused. If, for example, precedence in interpretation here, that is end with 000. If can be, for example, end with 0, end with 11, end with 01, and end with 000. That is 6-bit. When end to 0, that is internet, assigning authority. And when 2, that is ended to 11, that is local. And when end to 01, that is temporary or experimental. This means the packet with internet has a high quality. But this value is not used in internet now. Identification. That is 60-bit unique identification of a datagram from a host and incremented whenever a datagram is transmitted. We have flagged 30-bit here. First bit always set to 0, first bit. And defragment bit do not fragment. Say to router, don't fragment this segment and this datagram, because assembly of this have more time. And yes, I see you. And more fragment if we want. Will be explained later. That is fragmentation. Wait. Time to live, that is 1 byte. Specified longest byte bit for datagram is dropped. Roll of time to live field ensure the packet is eventually dropped when a routing loop occurs. For example, if we have set 1111111, that is 255, the maximum value of this. Sender set the value of this field, for example 64, and each router decrements the value by 1. When the value reaches 0, the datagram is dropped. This means not forwarded to other nodes, so that we prevent from loop. Protocol, that is 1 byte, specify the higher layer protocol used for demultiplexing the higher to higher level and higher layers. For example, in higher layers, it's ICMP, that is 1, one that is 00000001 in 8-bit or 1 byte. TCP is 6, IGMP 2, UDP is 17, and IP and IP encapsulation, that is 20 link, that is 4. UDP is 17 here. 0 0 0 0 1 0 0 0 0 1 here. Okay, header checksum, that is 2 bytes. A simple 60-bit line checksum which is computed for the header of datagram. A question: how this header checksum calculated? Do you know how this header checksum calculated? Yes, when we want, come back, when we want calculate this, here all fields 2 byte 2 byte, okay, added to each other. For example, first 2 byte here from first word, then second 2 byte, and so except this header checksum until here. All the field of this of header added to each other. Then we have once complement. Okay, we have once complement as of this compute once complement of headers field in 2 bytes, 2 bytes, 2 bytes. Then once complement of header field store here, store in header checksum, in sender, in receiver we add all fields of headers 2 by 2 bytes. What is the result? If no error, in the receiver we have all fields of headers. Yes, this is 0. Okay, this is 0. If all of these fields are header, that is 0, we have no error. Because when a number added to one's complement of number, okay, the added will be 0. Yes. Options. Security restrictions in options. Record the route, for example, each router that process the packet adds its IP address to the header. And timestamp each router that process the packet adds its IP address and time to the header for storing the timestamp of the header of the router. Loose source routing specifies a list of routers that must be traversed. This means, for example, for trust, for reliability. And strict source routing specifies a list of the only routers that can be traversed. Loose must be traversed, strict can be traversed. added to ensure that the header ends on a 4-byte boundary, that is padding. Padding dot are added to ensure the header ends on a 4-byte boundary. For example, if all is 62, 62 is not the multiply of 4, okay? We added this 2 byte, so that's 64. 64, that is multiply of 4. Here you can see IP module from upper layer protocol data and destination address added to this. This is IP, and we have from TCP, for example, and added data and destination address, and header adding module here. Header adding module added this header to the data, and go to processing module. Processing module send IP packet to forwarding module. Forwarding module used from routing table in router, and IP packet next hop interface can split this datagram into some fragments. Here fragmentation module send this fragment to the buffer, and here to the interface, and then to data link layer. And for fragmentation used from MTU table. MTU table is maximum transmission unit. In destination, from data link layer, IP packet give to processing model. Processing model give the IP packet to reassembly module. Reassembly module from reassembly used from reassembly table, and assemble this IP fragment to each other to reach to IP datagram. Here datagram give to the upper layer protocol. Okay, so IP fragment the datagram and give to data link layer, and give fragments from data link layer added to each other, assemble, and give to upper layer. Yes, data stored in payload. Yes, data stored in payload. Maximum transmission unit. Maximum size of IP datagram is 65,535, but the data link layer protocol generally impose a limit that is much smaller. For example, Ethernet frame have a maximum payload of 1,500 bytes Ethernet. But IP datagram encapsulated in Ethernet frame cannot be longer than 1,500 bytes. The limit on the maximum IP datagram size imposed by the data link protocol is called maximum transmission unit. Maximum transmission unit various data link protocol, for example, Ethernet 1500, 800 2.3 1492, 800 2.5 4464, in FTDI 4652, in ATM asynchronous transfer mode 9180, in peer-to-peer negotiated between sender and receiver. For example, we have IP fragmentation. What is the size of the IP datagram exceeds the MTU? IP datagram is fragmented into smaller units. What if the road contains network with different MTU? When we use from different MTU, we must fragment this datagram into smaller parts. For example, host A wants send a datagram to host B. You can see between host A and router we use FTDI ring, and between router as host B we have Ethernet. Maximum transmission unit in FTDI network is 4652 and in Ethernet 1500. Okay? Fragmentation. IP router split the datagram into several datagrams, and fragments are reassembled at the receiver. Where is the fragmentation done? Fragmentation can be done at the sender or at intermediate routers. The same datagram can be fragmented several times because, for example, next network may be lower maximum transmission unit size. Reassembly of original datagram is only done at destination host. So, fragmentation is sender or intermediate routers, but reassembly only in host or destination host. We can see here IP datagram, and that is header of this. Then go to router break this datagram into two fragments, fragment 1 and fragment 2. And each of them has a header. What's involved in a fragmentation? The following fields in the IP header are involved. Total length, that is with red color. Identification, don't fragment, more fragment, and fragment offset. Identification. When a datagram is fragmented, the identification is the same in all fragments. So identification shows the number of this datagram. Flags that don't fragment bit is set. This means datagram cannot be fragmented and must be discarded if maximum transmission unit is too small. This means if maximum transmission unit is too small, this datagram is not transmitted and is not fragmented. Because, for example, if fragmented, we need time to assemble it. But here, for example, speed important for me. More fragment bit set, the datagram is part of a fragment and an additional fragment follows this one. The following fields in the IP header are involved, that is fragment offset, offset of the payload of the current fragment in the original datagram, and total length, that is the total length of current fragment. For example, a datagram with size 2400 bytes must be fragmented according to an MTU limit of 1000 bytes. Okay? So IP datagram, we have a header length 220, total length 2400, identification 0xA428, that is an 60-bit, because identification with 60-bit, that is 4 hexadecimal number. Okay? A428, A428, 1010 4 0100 200 108 1000. Okay, that is 60-bit. But the MTU is 1000. So we have fragment this data 2400 into 3 fragments. The fragment 1 header length is 20 here, total length 1996, and the identification here, dot fragment 0 and more fragment 1. Dot fragment flag 0. If dot fragment flag is 1, not fragmented, but here is 0. More fragment 1, that is we have next fragment, fragment 2. And fragment offset, that is 0. Okay? The question. a question. Why 1994? Why 1994? No, 1994 total length. Because the M2 is 1000, okay? So that is less than 1000. Because this. Okay? Why no 1000? Why? Why this? Yes, because that is less than 1000. Maximum transmitted less than 1000. So then not be 1000. So the next, that is 1996, is multiplication of 4. Okay? Multiplication of 4. Here. Why here 100 for the next fragment? Header length 20, total length 1996, identification the same. Don't fragment 0, more fragment 1. And here fragment offset 122. Why? 122 multiply 8, because each segment has 8 bits. What is this? 9, 7, 6. Okay? Byte. 122, that is 976 byte. Okay? That is data. And when this data, that is data plus header, that is 20. Okay? The total length is 1996 here. So that 1996 is total length. But fragment offset is the data, not the header. Okay? So that 122. And next header, 192.168.1.2, subnet mask 255.255.255.0. Here we have 24 bits for net ID and only 8 bits for host ID here. And default gateway 192.168.1.1. What is the class? I say each byte is 1 byte between 0 until 255. Here we have 4 bytes, 4 until 1 byte 4 bytes, that is 32 bits. Class A begins with 0 and net ID is 7 bits and host ID is 24 bits. Class B start with 10, 40 with net ID, and 60 for host ID. Class C start with what 10, net ID is 21-bit and host ID is 8-bit. When, for example, in class A, we have a 2 exponent 7 network, okay? Networks and 2 exponent 24 hosts in each network. But in class C, we have 2 exponent 21 networks and 2 exponent 8 hosts. If number of hosts large, we can use from class A, number of hosts in each network. But each number of network is large, we use class C. Class D starts with 1110 and 28-bit for multicast address, and class E starts with 1111 and that is reserved. But in class B, with class B, we have 2 exponent 40 minus 2 networks. Why? What minus 2? In class B, 2 exponent 40 minus 2 networks. Yes, because 0, 0, 0, 0. Yes, that is localhost, and 1, 1, 1, 1, 1, 1, 1, 1. That is for broadcast. Yes. What is 192.168? What class? Here. 1, 1, 1, 2. Yes. 192. That is 192 equal 160 for 26, 28 plus 64. Okay. So 11000000. Okay. Here 192. So that is start with what 110. So that is class C. We got to start with this. Class A, that is network ID between 1 until we have 4 octet in class A between 1 to 128, octet to 0 to 455, 0 to 2055, 0 to 2055. That is between 1000 until 128.27.255, 255, 255. Okay? Why 0, 0, 0, 0? Yes, that is localhost, not class A. Okay? That is localhost. So that here start with what 1000. Class B start with 10. That is 128, 000 to 191, 255, 255, 255. This is start with 10. When 0, 0, 0, 0, 0, 0, that is equal 128. Okay? And then 1, 0, 1, 1, 1, 1, 1, 1 equal 191 here. Because class B starts with 10. 110 in class C. 110 0, 0, 0, 0, 0, that is 192 until 110 1, 1, 1, 1, 1, 1, that is 223. Okay, here 223. And why currency from 1 to 254? Because here that is for broadcast here. And class D start with 1110, so that 0000 224 and 1110 1111, that's equal 290 239 here. And class E start with 1111, so that 0000, that is 240 here. Because 60 plus 32 plus 64 plus 128, that is 240, okay? And class A start with 1111, and the end 1111, that is 255. But here the last octet between 100 until 249, because 0 can be for local host in the octet 4 and 255 for the broadcast here. Okay, this is the end of this lecture, and we go to the lecture 3 for the next session. Let me here upload the lecture 3 that is for next session. In next session we go to IP version 6 and study that. Okay. Do you have any questions, students? Do you have any question? Okay, send me papers about the topics that we say in the previous session to work on the your paper and prepare PowerPoint of this. Thank you for attention and goodbye.